Hello, Avinash. We will wait for 5 more minutes to see if anyone other joins. Then we will start. Okay.
Okay.
Hello, Avinash. Are you able to see the screen?
Yes, sir.
The slides are moving.
Yes, sir. All okay.
Okay. So, first of all, I will introduce myself to you. My name is Ganesh Shankar Bhandari, and I am doing my PhD from IIT Roorkee, and I am a PMRF research scholar. So, I will be here to take a live session every Sunday from 4 to 6 for your course Principles of Extractive Metallurgy. Course instructor Professor Tarun Kumar Kundu from IIT Kharagpur. So, in this live session, we will discuss some numerical problems or maybe some MCQ type problems which will help you in solving your assignments which you will get during your whole course. Okay, so in every session we will revise the previous week lectures first, then we will go for the solving of problems. Okay, so first of all we will see what Professor Kundu has taught in the last week lectures. So, first of all, the course is regarding principles of extractive metallurgy. So, I hope you have already learned about the extractive metallurgy of iron and steel making. So, this course is basically about the extractive metallurgy of non-ferrous metals. Okay, if you have not learned about the steel metallurgy, then you will get a course maybe in upcoming semesters for iron and steel making. But this course is all about the extractive metallurgy of non-ferrous metals like copper, aluminium, tin, lead. Okay, whatever the non-ferrous metals which are basically used in the day-to-day applications. Okay, so first of all, we will start with the introduction to extractive metallurgy. So, extractive metallurgy is basically a science and or we can say art of production for extraction of metals from ores. So, basically, ores are like naturally occurring compounds which we can denote as stones. Okay, or wherever you find some stone or some mineral, it is like it can be a ore if we can economically extract some elements from that particular stone or particular mineral. Okay, like for example, if we talk about dolomite or we talk about limestone which we are using as a marble material. Okay, so from limestone if we can economically extract the calcium material out from that limestone, okay, that can be considered as a ore, otherwise it will be considered as a mineral only. Okay, so uh, nowadays we are talking as we have already talked about ores. Nowadays we can extend this extractive metallurgy part to the secondary recycling also. Okay, nowadays you have seen we are talking about the recycling of waste materials, like we are majorly talking about e-waste recycling, we are talking about battery recycling. So those materials can be considered as a secondary ore material or secondary sources for particular elements recovery. Okay, so extractive metallurgy uh, includes them also. Okay, so extraction of metals from ores or concentrate, scrap or other sources, whatever you can think, and refining to the level of purity suitable for commercial use. Like if we talk about copper, okay, so we need copper with a purity of at least 99% so that we can use them as a wire. Okay, electrical for electrical conductivity. So raw material we can process it with the help of physical and chemical transformation, and various separation steps will be there. Then we will get bulk metal, and from bulk metal we will go for the physical or chemical transformation steps for that particular bulk metal to refine that material. Like for example, if we are talking about copper, okay, so we will find a ore of copper. For example, we have found chalcopyrite. Okay, so in chalcopyrite, the copper percentage will not be more than 0.8% or 1%. Okay, but you have to reach to a purity of 99%. So from 1% you will go for some physical or chemical transformation processes to increase that concentration of copper material inside that chalcopyrite ore. So for example, we will go with froth flotation process or we will go with some roasting process to increase that 1% of copper material to 24 or 25%. Okay, then from 25, we will go for some roasting process or some pyrometallurgical processes to increase that material up to 98 or 99%. Then we will refine that material to get a purity of more than 99%. Okay, so during this whole process, we are going to recover this copper material. Apart from this copper material, during the whole process, we can recover some other elements also, which for which copper is acting as a scavenger. Okay, so these materials are coming with the copper ore itself. Okay, like we can say we can get some gold material, we can get some lead, or we can get some silver also from during the whole refining, or we can say extraction process of this copper material. Okay, so extractive metallurgy is the continued manifestation of the mastery of natural resources to transform materials for practical purposes from prehistoric to most advanced application. So, if we talk about the history of extractive metallurgy, that can go beyond up to 10,000 years before. Okay, from prehistoric times, we are using the extractive metallurgy to refine the metals from the ores or minerals. Okay, and we are converting them into useful applications. So, there are process trends in extractive metallurgy like continuous or semi-continuous processing. It can reduce energy and environmental impact and improve throughput control, increase process intensity, or process integration or recycling process, which we are going for the secondary materials like e-waste or batteries or some other materials are there. So we can recycle them to recover back the materials whichever which is present inside them. Okay, then we talk about clean production, like in present scenario we are mostly talking about CO2 emissions, we are talking about net zero carbon emissions, and we are talking
Sir,
about treatment of effluents. Yes,
sir,
yes.
sir, what is the meaning of integration of primary and secondary processing?
Integration of primary and secondary processing is like when we talk about the first thing is primary is like ore processing. Okay, and then secondary is your e-waste material processing. So some companies, what they are doing, they are integrating the both processes. Like for example, you can search Umicore. Okay, there is a company in Belgium, that name is Umicore. Okay, so that is mainly into the recycling of battery materials. Okay, so what they are doing, they have developed their process in such a way. Okay, so they are feeding at the same time the primary ore material and the battery material also in the same furnace. Okay, so that they can economically extract the metallic values from both of them. Okay, for example, if we are going for the secondary material processing alone, okay, sometimes it is not possible to extract the materials economical. Materials extraction from these secondary sources will not be economical. Okay, so they have incorporated that material as a feed material during their ore processing itself. So it is known as integration of primary and secondary processing. Okay, understood.
Yes, sir.
Okay, then clean production, we talk about the net zero carbon emission, and we talk about the treatment of effluents generated during the whole processing. Like if we are going for the hydrometallurgical process, like acid leaching. Okay, so we have to treat the effluent also, because we cannot left that highly basic or highly acidic effluent just like that. We have to treat that up to neutral level, then only we can discard that material. Okay, then flexibility of the processes, like adaptation of changing input or output requirement within existing plant. So it's like when we are going to build a plant. Okay, so we have to seek flexibility also. Okay, it's not like for a whole 5 year or 10 year tenure you are going to get the similar material or similar concentrate during for the processing of that particular metal. Okay, so you have to build a plant with such a flexibility so that you can adapt the changing input material. Okay, like you have started a plant 10 years ago. Okay, so that time the copper percentage in ore was around 1.2 or 1.5%. Okay, and nowadays it has decreased up to 0.7 or 0.6%. Okay, so you cannot treat the same material with the existing plant facilities which you have built 10 years ago. Okay, so you have to incorporate some changes in the existing plant so that you can go for the processing of that 0.6% copper material. Okay, so that there has to be flexibility in the processing, or there has to be flexibility for changing the input or output requirements of the existing plant. Then there are driving forces for technology development like safety, sustainability, it has to be environment friendly and economical at all. It has to be economical. So there are different properties of metals like solid. They are solid state at room temperature except mercury, and they have shiny appearance, ductility and malleability, and they are good conductors of electricity. They are good conductors of heat, and they are strong and tough. Okay, and uh, they also have the higher density due to the close packing of the atoms inside these metals. Okay. Then properties of metals. There are metallic bonds. Then there are class. You have already read about the periodic tables during your 11th or 12th. Okay. So they have classified the elements based on their electronic structure of atoms. Like they talk about S block element. They talk about P block, D block. Some are rare earth elements. Some are metalloid, non-metals, gases. So there are different categories among them. Okay, so we generally talk about alkali metals, alkaline earth metals, transition metals, and they all have different properties. Like if we talk about transition metals, so they have a unique property so that they can change their oxidation state. Okay, in the last D block, in the last D cell, they have different valency states. Okay, so they can change their oxidation states. Like if we talk about iron, iron can change their oxidation into three different forms: plus 2, plus 3, and Fe metallic, which is having oxidation state of 0. So it's like hematite is having plus 3 oxidation state, magnetite, or we can say boostite, that is generally FeO, it is having plus 2 oxidation state. And if we talk about Fe metallic, then it is having 0 oxidation state. So this comes under the category of the transition metals. Then there are rare earth elements. So why they called rare earth? Okay, because they are very rare. They have very rare occurrence in the earth crust. Like they are occurring in the earth crust with ppm levels. Sometimes you can find you can find only 50 or 100 ppms. Okay, so that's why they are called rare earth elements. But in nowadays life, when we are talking about numerous electronic applications, so the importance of these rare earth elements increase uh, many folds. Okay, because any electronic structure you can think it cannot work without without the possibility without these rare earth elements. Every single electronic element consists them. Maybe sometimes it can be in very low quantity, or sometimes it can be in very high quantity. Okay. Then material scientists define metals as those elements which have no electronic energy band gap and whose electrical resistivity increases with the temperature. Then there are economic classifications of metals like ferrous and non-ferrous. If we talk about the difference between ferrous and non-ferrous metal
Sir, please explain it
production,
how to increase electrical resistivity with temperature.
because what happens when you are going to increase the temperature. Okay, so when we talk about metals, they are tightly packed structure. Okay, and when you are going to increase the temperature, so there will be some like bond stretching will be there. Okay, so you will get some free atoms with the help of that temperature. When you are going to increase the temperature from 50 degrees celsius to 700 degrees celsius, if you read about the iron making. Okay, then we talk about the transformation of that iron material from one phase to another phase. It's like changing their structure from bcc to fcc. Okay, at room temperature it is generally bcc structure. Then at 750 degrees celsius or 800 degrees celsius, it is getting converted into the fcc structure. So during that whole processing, okay, what is going to happen, you will get some loose atoms inside that material. Okay, and that will help to increase that electrical resistivity. Okay, Then we when we talk about economic classification of metals, ferrous and non-ferrous. Okay, so if we compare the ferrous and non-ferrous production scenario, so it's like when we talk about steel, we talk about around 150 or 140 million tons of production, while the highest non-ferrous metal production which we talk about is of aluminium. Okay, and we are talking about the production of aluminium only in the range of around 10 to 20 million tons per annum. So it's like 10 times gap between the ferrous production and the non-ferrous production. If we are talking about the production of all non-ferrous metals, then also it will not uh, then also it cannot be compared with the production of the ferrous metal. It is like 130 million ton, and if you talk about the all non-ferrous metal production, it will be somewhere in the range of around 30 to 35 million tons only. Okay, then there are economic classification of metals. So
Sir, how to
top
identify ferrous and non-ferrous metal?
ferrous metals is when we talk about ferrous, we only talk about the iron material. Okay, and when we talk about the non-ferrous metals, so it is like aluminium, copper, then your vanadium, whatever is you can see, those are non-ferrous metals. Generally, ferrous metals consist of iron, chromium, nickel, which is having like we can say in simple terms, we can say the materials which are having ferromagnetic properties mainly. Okay, that can be considered as crudely considered as a ferrous metal. But generally, we only talk about the iron in case of ferrous metals and its alloys. Okay, we talk about steel, we talk about mild steel, we talk about stainless steel. So these are ferrous metals. Okay, and all others are non-ferrous metals. Okay.
Yes, sir.
Then there are economic classifications of metals like top six base metals production is in the range of aluminium, then copper, zinc, lead, nickel, tin. They are all non-ferrous materials. Base or primary metals are non-ferrous, meaning they contain no iron. They are more abundant and sometimes easier to mine, so their prices are generally lower than precious metals. Okay, so whatever the alloy or metal you are considering without no iron content, okay, that will be considered as a non-ferrous metals. Okay, then there are so these six are considered as the base metals because whenever we talk about the alloy making, okay, so these will be on the base of it. Okay, when we talk about aluminium, we talk about different categories of aluminium alloy, we talk about different categories of nickel alloy. So the higher composition of that alloy will contain these six metals. Okay, then there are precious metals like silver, gold, palladium and platinum, because the occurrence of uh, these materials in earth crust is very rare. Okay, and or we can say the beneficiation of processing steps are so much costly, so the cost of these materials gets increased. Okay, so gold and precious metals grab the headlines because of their rarity, and their production shows just how rare they are. Okay, as we can see, if we are going to compare with aluminium, so aluminium production in 2019 was at around 64 million metric ton. Okay, while silver was only 27,000 metric tons. So you can see the difference. Due to this rare occurrence, the price of these precious metals are very high. If we compare with aluminium, you can get aluminium at around 400 or 500 rupees per kg, while the price of silver is at around 90,000 rupees per kg. Okay, so these are precious metals. Then there are commercial classifications of non-ferrous metals. Yeah. So based on commercial classification of non-ferrous metals and metalloys, we can divide them into different groups like primary materials, which is considered as copper, lead, zinc, tin, and nickel. Why we call them primary material? Because they are extensively used, or we can say after iron, they are mostly most used alloys or elements in the periodic table. One second, somebody wants to join. Okay, then there are secondary materials like arsenic, bismuth, antimony, cadmium. So these metals are mainly used for the alloying of the primary metals. They are used as like in some percentage like 2 or 3 percentage doping or in these primary materials, and we use them to make the alloy formations. Then there are light metals, then precious metals, gold, silver, platinum. Then there are refractory materials which can sustain at high, which are having very high melting point. At least the lowest melting points of these refractory materials is around 1650 degrees Celsius. Sometimes they can go up to 3000 or 3200 degrees Celsius also for melting point. Then there are scattered materials. So why we are calling them scattered? Because they uh, don't have any specific ores. They are scattered in the different minerals, or we can say ores. So during the processing, we found them as a secondary material. Like if we are talking about copper, okay. So during the copper processing or during the aluminum processing, aluminum ore processing, we can found these scattered materials. Like if we are talking about gallium or indium, we can found them in the bauxite ore or aluminum ore. During the processing of aluminum, we can found these materials in ppm levels like 200 or 300 ppm only. Then there are radioactive materials like radium, thorium, then uranium. Then there are rare earth materials. These the major property of these rare earth materials are they always occur together. Okay, so if we talk about the occurrence of rare earth materials in India, you have heard heard the name of monazite sand. Okay, that is found at that is found at the found in the coastal areas of this western west eastern region. Sorry, uh, so there we can found the monazite sand, and this monazite sand contains some thorium content also. So in India, no private company is allowed to process this monazite sand because it also contains the thorium material, which is radioactive material, and it contains the rare earth elements inside that sand, like neodymium, praseodymium, or you can find them cerium or lanthanum in that monazite sand. Then there are ferroalloy metals like chromium, manganese, silicon, or boron. Why we are calling them ferroalloy metals? Because these elements are generally used as a alloying elements during the stainless steel production, or we can or in the iron production. Then alkali metals, these are soft and highly reactive, and they can react with the air also if these are in the elemental form. So we can see there is lithium and sodium, and if we consider the electronegativity series, so they are on the top of that electronegativity series. Like lithium is highly reactive metal, and then comes the sodium and potassium. So these are highly reactive metals. Then there are alkaline earth metals. These have higher melting point and less reactive than the alkali metals. Okay. Then according to the use of primary metals, there are if we talk about copper, it is generally used in electricals, then in engineering and transport, buildings, then lead, zinc, tin. They have different uses. Okay. Then if we talk about this titanium, okay, titanium is generally used as a alloying element in making the jet engine alloy material. Okay, these material have a unique property, like these have a very high creep resistance, or they can sustain higher temperature. Okay, so these are used in the making of jet engines, and they are very in if we talk about density, they are low in density. Okay, then you can read these things. Then, yes, rare earth metals. So, when we talk about the electronic materials, then we talk about the rare earth elements. Okay, so let's consider a hard disk magnet. Okay, hard disk. You know hard disk or SSD. you use in your laptops, or you consider a pen drive. Okay, so these hard disk contain some magnet inside that hard disk. Okay, for storing the for storing capacity. So these magnets are basically rare earth magnets, and it contains neodymium. Sometimes it can contain praseodymium. So these are the uh, major use of rare earth elements. And in today's scenario, if we talk about the alloy steel, okay, in some alloy steels they are using rare earth elements as a alloying material, like they are using cerium, they are using lanthanum in the steel making for the alloying purposes. And you have seen that fluorescent lamp, huh? You know about fluorescent lamp, CFLs? Hello.
No, sir.
No, sir.
Uh, uh, Nowadays you see these tube lights. These tube lights are LEDs generally. We talk about LEDs, light emitting diodes. So these tube lights, what we found nowadays, it is LED. Okay. In if we talk about 5 years 5 years behind, okay, 5 years ago we were using tube lights which were not LEDs. Okay, so those tube lights were containing a phosphor material inside those tube lights. Okay, so that phosphor material is basically a rare earth compound. Like we can say that has different composition for different lights. That has different composition, and that were containing around 30% of rare earth elements inside that tube light. And those tube lights were also having some mercury content inside those tube lights. Nowadays we all are using LEDs, and these LEDs also contains the rare earth elements, the light emitting diode chip, which is basically a semiconductor materials. These are made up of the rare earth elements. This contains the coating of rare earth phosphors on that material, and the chip inside these light emitting diode is gallium nitrate chip. Okay, and gallium is very rarely occurring material. Gallium, we don't find any particular ore of gallium that is uh, recovered as a byproduct of the aluminium processing. In the aluminium ore, we found gallium in some ppm levels like 50 or 100 ppm only. Only for the recovery of gallium, we are relying on the only on the bauxite ores. Okay, so that's why nowadays people are talking about the recycling of these e-waste materials, because these e-waste which we are generating day by day, it is containing high amount of these rare earth elements. And as the name suggests, these are very rare in earth crust, and we have to rely on the recycling of these e-waste material to so that we can recover these rare earth values, rare earth elements values again, and we can use them in the new electronic material manufacturings. Okay, then there are important use of alkali metals also, like lithium is used in batteries when we talk about the mobile phone batteries, or we talk about the laptop batteries. So these batteries are generally lithium ion batteries. Okay, and nowadays they are trying to changed the concentration of lithium to the sodium. So they are talking about sodium ion batteries. Then lithium is also used as a used in medicine to treat mental disorder. Okay, for if someone is taking the medicine for the depression. Okay, so that medicine will contain some amount of the lithium salts. Okay, then sodium, it is used in the street lamps to give orange glow, and it can be alloyed with potassium to make material, or in day-to-day life we use sodium as sodium chloride, normal household salt. Then potassium, it is generally used as a fertilizer material as potassium nitrate. And India, if we talk about India, the occurrence of potassium is very low. We generally used to import the potassium from this Russia, and for our fertilizer manufacturings. Then important use of alkaline earth metals like magnesium is generally used as a magnesium is can be used as a alloy material in building engine blocks or alloy wheels. So what this magnesium provides, this magnesium if we are going for the alloying of this magnesium material inside our steels, so it will provide a unique property to the steel that steel will be having very high strength with very low weight. Okay, so that can be used as a engine block material or alloy wheels. Okay, then strontium nanoparticles can be used for gas sensing, drug delivery, treatment of wastewater, antimicrobial agent, while beryllium can be used in manufacturing the special alloy steel, which can be used in satellites and aerospace structure manufacturing. Then steel production, this thing you can read just. Then if we talk about the non-ferrous metal production in India, so there are two, three major companies which are producing the non-ferrous metals like Nalco is producing the aluminium material, Hindalco is also producing aluminium, and sometimes it produce copper also. Then Balco is producing aluminium, then Vedanta is there for production of aluminium and copper. So the installed capacity of copper production in India is around 1.08 million ton per year. Okay. And if we are going to compare it with the ferrous material, okay, if we are going to compare it with iron, so iron is at around 140 or 150 million ton per year. So you can see a huge difference between them. And then India's overall zinc smelting capacity is around only 0.92 million ton. And with the zinc, there comes lead. So zinc and lead will always occur together. They have a unique property. They will always occur together. So the company which is producing zinc, it will also produce. 1 second. Yeah. So the company which is producing the zinc, it will always produce the lead also because the ore occurrence is at similar place. When we find zinc, we will definitely find going to find the lead also. Okay. So then comes to next lecture. Yeah. So occurrence of metals. So chemically active elements always occur in the combined stage. That is in the form of stable compounds like we can say minerals that contains different elements, and less reactive metals like platinum, gold, they occur in free native state. When we talk about the noble metals, okay, so platinum and gold, they are not most friendly with the oxygen. Okay, so you will find them in the native state only, like in their metallic state only. If while if we talk about the iron or sodium or more reactive metals like magnesium, you will found them in the state of oxides, or you can found them in state of carbonates or maybe sulfides. So the states of occurrence of these elements in nature occurs according to depends on their reactivity. If they are more reactive, okay, so they are tends to make compounds with some other metals. Okay, so if you talk about copper, it is more friendly with the sulfurs and oxides, so you will find them in the state of copper sulfate or copper sulfide. If we talk about iron, it is more friendly with the oxygen gas. Okay, so it will convert them inside. They will you will find iron in the states of hematite or magnetite in Fe2O3 or Fe3O formation. Okay, metal that occur in the combined form exist as their oxides, sulfides, carbonates, phosphates, and silicates, etc. And deposits in earth crust is the most important source of metal bearing minerals. While we can go for seawater also, which is known as deep sea nodules, that can be also a source of large number of elements. Like we can if we talk about these deep sea nodules, uh, then we can, according to scientific research, we can recover a better amount of cobalt or nickel, those D block elements. Okay, that can be recovered with the help of these deep sea nodules. Then there is scrap metals, which is considered as reclaimed or recycled, can also be another source of metals. Then relative abundance of elements on earth crust. If we talk about the abundance of these elements, okay, so aluminium is at around 8.3, then iron 5.6, calcium 4.1, and as we are going lower in the series, we can found gold here. Okay, you can see gold here. So the abundance of this gold material is only 0.0012 to 0.01 ppm. So now you can think why, now you can see why the prices of gold is so much higher. It is nowadays it is having a cost of around 70,000 or 75,000 per 10 gram material. Okay, so the occurrence of this element is very low in earth crust. That's why it is having very higher prices. Okay, and when we talk about the rare earth elements, then they are having a occurrence of around 1 to 10 ppm only. Okay, then if we talk about this metals in C nodules, okay, we can see there is manganese, there is nickel 0.988%, there is cobalt 0.35, then copper, and major components are manganese and iron content. So now we will talk about minerals and ores. So minerals are like naturally occurring inorganic solids having distinctive physical properties, and it contains um, different elements or having definite composition consisting of one or more metals in association with non-metals. Okay, so there are three different things. One is, first is rock, then mineral, then ore. Okay, so at the same times we talk about three different things. Rock. Okay, so rock will also have some metals or non-metals inside that content, but it will not be having a defined composition, or we can say defined formulation. Okay, so that anything which is occurring in the earth crust is not having defined composition or not consisting any metal inside them, will be considered as a rock material. Okay, then second comes mineral. So mineral is also is a type of rock. We can say mineral is a type of rock which is having a defined composition or a defined formula which consists one or more metals in association with the non-metals. Like for example, limestone. Okay, so limestone is having a metal which is calcium, and it is also having the non-metal which is carbon and oxygen. So it is having a formula of CaCO3. Okay, calcium carbonate. Then we can say all minerals can be rock, but all rock cannot be a mineral material. Okay. Then third we come at ores. So ores can be considered as a mineral. Okay, which from which we can extract one or more type of metallic values in an economically viable manner. Okay, like if we talk about calcium, just we have talked about calcium carbonate. Okay, so from calcium carbonate, if we are going trying to recover the calcium metal from that calcium carbonate, okay, it will not be feasible, or we can say it will not be economically feasible. Okay, so that can be considered as a mineral only. While if we talk about chalcopyrite, which is CuSO4, okay, copper sulfate, so which can be used to extract copper metal in an economical manner. So that can be considered as a ore. So we can say all ores can be called as a mineral, but all minerals cannot be a ore material. Okay, so now comes gang material. Okay, so what is this gang material? Whenever we are going to find these minerals or ores, so when we talk about ore, or we can say when we talk about, for example, we talk about chalcopyrite ore. So that will be having only a copper composition of 0.4, zero point 0.8 or maximum 1%. Okay. So what is other 99% inside that particular ore? So that 99% is basically the gangue material. So these are defined as some minerals which is non-metallic materials or pyrites usually worth. So they are usually worthless. Some minerals associated with a deposit in ore are not useful from the point of view of metal extraction. These are known as gangue material. So uh, so what these gangue materials can be? Okay, so here comes this abundance, relative abundance of elements in earth crust. So we have talked about the abundancy in the range of 1 to 10%, which is consisting aluminium, iron, calcium, sodium, magnesium, and potassium. So if we talk about copper, then it is around 0.001 or 0.01% only. Okay, so what can be a gangue material? Can you think any answer, Avinash?
Yes, sir.
What can be a gangue material according to, if we are going to see the abundance of these elements in the earth crust, what can be a gangue material? Whatever will be in the more abundance in the earth crust, that can be a gangue material. When we are talking about we are talking about two things. One is having one is 10 at around one is 10 kg, one is only some 100 grams. Okay, so if we are talking about a ore which is having only 1% of element inside them, okay, so what will be the gangue material? The amount, the material which is coming in the amount of 10 kg, that can be a gangue material to the material which is having only 1 kg composition. Okay, so more the abundancy, so aluminium, iron, calcium, or silica material, that can be a gangue material to any of the minerals or ores present in the earth crust. Okay, then here comes the common metallic ores or sources like iron can be main source of iron is magnetite, hematite, siderite, limonite. So these are having different formulas, like magnetite is basically oxide, then siderite is iron carbonate, and limonite is iron hydroxide. Then copper can be found as a native copper, chalcopyrite or chalcocite. Aluminium can be found in dispore or gibbsite form, or it can be found in kaolinite, which is basically a clay material. Then lead is galena, cerussite, angelicite. So there are different metals and their metallic ores. Okay, so and cobalt can be found as found as cobaltite, and these ores will come these ore will come with different gangue materials. Okay, the if we for example, if we talk about iron, okay, so iron can be found as hematite material, Fe2O3. Okay, so in any ore the content of Fe2O3 will be at around 62 to 65% or 60 to 65%. rest of uh, Rest quantity will be silica or aluminium material. Okay, then common metallic ores or sources that you can read. Then there are common types of ores, like it can be in the different form. It can be native elements, which is found for gold, silver, or copper. Then there are sulfides of typical examples: galena, which is a ore of lead; then sphalerite, which is a ore of zinc. Then there are silicates, zircon, beryl, thorite, borates, then carbonates, phosphates, that thing you can see. Then abundant compound form of metals. This is not much important things. Yes. So this okay. So you can see this circle. So in the middle there are carrier metals. Okay. So manganese, iron, aluminum, magnesium, lithium, uh, tin, nickel, copper, lead, zinc. These all are carrier metals. So it can be considered as bulk metals, but generally of lower value.
Sir, use of carrier metal.
So your carrier metals like when we are talking, for example, if we take this zinc and lead, okay, so these are acting as carrier metals for these all elements. Okay, these gold, silver, gallium, germanium, indium, cadmium. Okay, so they will occur together. Okay, but we are primarily going for the primarily going for the extraction of zinc and lead. Okay, but apart from the primary extraction of zinc or lead from that particular ore, we can consider the extraction of these gold and silver values also from that particular ore. Okay, so this is the main role of carrying metals. So these carrying metals will come up with some other metals also. Okay, sometimes these other metals can be economically extracted from the carrying metal, or sometimes they are. If we can extract them economically extract them from these carrier during the recovery of these carrying metals, then it is good. If we cannot extract them economically, then we will end up with a very new area. So, for example, if you talk about zinc or lead, okay, then our pellet become they are together. Okay, so when typical zinc and lead ore will consist of around 40% of zinc and 30 to 40% of lead. Other 20 to 30% will be your iron content, manganese, and this silicon material. Okay, that will be considered inside those 20 to 30% material. Apart from that, it will also contain some ppm level of gold and silver materials also. So now, if we talk about the economic extraction, okay, so the value of gold is high. Okay, you can see that around 70,000 per 10 gram. Okay, so for ppm level also, if you are having an ore which is having ppm level of gold, okay, you will try for that. You can't extract that gold material at ppm level also. But if we talk about iron, okay, iron is having a value of around 50 rupees or 40 rupees per kg only. Okay, and if some material is having 10% or 20% iron, 20% iron also, you will not consider it for extraction of iron. Okay, because that is not economical for you, because it is having very low value. Like for that for the extraction of that 10 or 20% iron, you are going to loss around 80 or 90 rupees. Okay, and you are getting a value of only 50 rupees per kg. So what is the point of extracting that particular iron from that ore? Okay, so these are core elements that end up in residue chemistry. So critical metals are basically metals inside a particular ore that contains other elements which can be economically extracted or cannot be economically extracted. Okay, anything else?
one example of hydrometallurgy. One example of hydrometallurgy.
One example of hydrometallurgy. If we talk about hydrometallurgy, we can see the recovery of lithium from the particular ore, or we can consider hydrometallurgy in copper processing also. In some ore, like if we are going with the copper sulfide ores, okay, then we can go the hydrometallurgical processes. We just have to leach it out. Okay, if it is containing very low amount of copper, like if we are talking about chalcopyrite, it can contain a copper amount of pound. And if we talk about copper content of 0.2 or 0.3% only, okay, then it is easier to go with the hydrometallurgical process rather than go for the pyrometallurgical process. Okay, so we go with the leaching process, and whatever liquid we are getting, it will dissolve the copper inside it. We will get the dissolved copper inside that liquid, and from that liquid, in the help of electrometallurgy, we can extract the copper out in the form of copper metal. Okay, in the form of steel. By electrowinning or electrofying process. In our lecture, we will talk about the copper metal processing. There will be for example the pyrometallurgy process. Okay, then many steps which are involved during these hydrometallurgical pyrometallurgical processes are mineral beneficiation, in which we are going for ore concentration, like in case of copper we are getting 1% ore, then we have to increase it up to 25 to 30%, and from 25 we have to increase to 65%, so that we can use it inside the pyrometallurgical process. Ore concentrate treatment, then metal separation, then reduction smelting, conversion of electric processes. At last comes we come at refining process, like we are getting a copper grade of around 90 or 99%. Most of the application we require copper grade of the grade of 4 nines, 99.9% or 99.99%. So for achieving that particular grade, we have to go for the refining of that material. Okay, then chemical aspect of production, these treatment that can be thermal, both of lithium, okay, that you can be, or we can discuss it in further lectures, that you will understand that. Okay, okay. So principle of extractions generally depend on two three things. One is the reactivity. Okay, for reactivity we consider the electronegativity series, or we can say EF series. Okay, so you can see upper part where reactive elements, and lower part they are very reactive elements. So this EMF series will be used to process of these metals. Okay, because with when we talk about EMF series, okay, so reactive elements we need higher energy to get converted into that in the reactive. But if we talk about gold or platinum, okay, sometimes we can get them in the negative state only. So we don't require any processing to get them converted into the metallic values. Okay, and like we can see from lithium to silver, they have they can react easily react with oxygens, then lithium to that they can easily react with dilute acids, and lithium, potassium, carrying calcium and sodium can
Sir,
react with water also. Okay, they can
sir,
they also
lithium,
react with,
potassium,
yeah.
and sir, lithium, potassium, and sodium also in one group. But why lithium and sodium very reactive uh, to sodium?
Lithium is very reactive to sodium. Okay, because lithium, if you consider this lithium, it is having on one, it is very periodic table. Lithium is at 3. Okay, so it is having
नहीं नहीं, वो सर 11 हो।
Yeah. Okay. So sodium is having two or three cells. Okay. So we require more energy. That's why it is reaction energy is so much high. Okay. So they can easily react with water, lithium, potassium, barium. We in 11th or 12th we have done, we might have done some experiments. Uh, like sodium, we used to kept it inside kerosene oil. If
Yes
sodium
sir.
metal is there, we cannot kept it in air. Okay, otherwise it will get dark because it is so reactive that it will react with air also and it will get burned up. Okay, or if you are putting it in kerosene oil, then it will not get react. Okay, and this MFCs and their metal activity is similar. There is one in the diagram that you are going to require during this whole lecture series. Okay. So aluminum diagram tells us this shows us the stability of metal bearing compound at standard conditions. Delta V naught versus temperature. So what delta V naught tells us? Any answer? That not negative, what will happen? If we are considering some reaction and delta V naught is negative or delta V naught is positive. So delta V naught is basically gives free energy which tells us the spontaneity of particular reaction. So if delta G naught is negative for a particular reaction, okay, that reaction can happen spontaneously at that particular temperature. Okay. Or if delta G naught is positive for a particular reaction, it means that reaction cannot happen at that particular temperature. There might be chance if you are going to increase temperature, okay, so that delta G naught of that particular reaction can get negative at some point of temperature. But if if we talk about the reaction of lithium and carbon, room temperature, okay, so the delta G naught value of that lithium metal and carbon reaction is very much negative. Okay, so that spontaneously get converted into lithium carbonate. Okay, any reaction which is having delta G naught at will not get that particular temperature that can go in the forward direction. Otherwise, can go the forward direction. Okay, so what element diagram tells us is tells us the affinity of element for oxygen with respect to temperature or affinity of elements for other non-metals like sulfur, carbon, nitrogen, fluoride, or chlorine. Finally, we go with the delta G diagram. Generally, by element diagram, we go with the oxygen content only, affinity of oxygen, but we can create an element diagram for the affinity of elements for other non-metals also like sulfide, carbon, nitrogen, chlorine, or fluoride materials. Okay, that you can make according to your according to the different delta G calculations. Okay, so it is there are four courses to we have to reduce the size, then we can go for beneficiation, then preventive treatment, post-processing, or we can directly go for the hydrometallurgy or pyrometallurgy process. And hydrometallurgy process will generally go in the leaching process, some acid or basic leaching, then solid liquid separation, then we will get leach liquor, and from that leach liquor, for recovering the particular heavy metal values from that leach liquor, we can go with different processes like adsorption of charcoal, solvent extraction, ion exchange, or precipitation or cementation processes. There are different types of processes. And after precipitation, we can go for electrolytic reduction or some other refining processes. And in pyrometallurgical processes, there is compound intermediate and chemical reaction. No, there is
Sir,
no, this don't have to be chemical reaction.
sir,
Pyrometallurgical process, yes.
Sir, if delta V will be मतलब zero, तो व्हाट इज ए कंडीशन, मतलब इसको किस में कंसीडर करेंगे यदि डेल्टा जी जीरो होगा तो?
डेल्टा जी जीरो होगा तो रिएक्शन को स्टॉप है वहाँ, वो आपको पता होगा, इट इज नॉट गोइंग इन फॉरवर्ड डायरेक्शन, इट इज नॉट गोइंग इन बैकवर्ड डायरेक्शन, इट इज केप्ट एट पर्टिकुलर प्लेस। डेल्टा जी अगर जीरो है किसी पर्टिकुलर पॉइंट पे, तो इसका मतलब ये है कि अगर तुम्हें वो रिएक्शन को हैपन कराना है, इफ यू वांट टू get that reaction happen, then you just have to increase your temperature a little bit. Okay, so that like delta G naught is a function of temperature. Okay, so with the change in temperature, the delta G naught value will get changed. Delta G naught equal to delta H minus T delta S. You have read in maybe thermodynamics. Delta G naught
यस सर,
equal to
इंट्रॉपी
delta H
इंट्रॉपी।
naught delta H minus T delta S. So it is a function of
यस सर,
temperature.
एंट्रॉपी।
Because delta H and delta S will not get changed. For a particular reaction, entropy will remain same and your entropy will remain same. What will change? The temperature. You can change the temperature of that particular reaction. With the help of temperature, you can get your delta G negative or positive, whatever the reaction you want. If you want to reaction to be happen, then you can increase the temperature and it will get into very negative zone.
ओके सर।
Okay, that you can see. There is a fluid approximation of copper from low grade sulfide ore. Okay, then in the introduction that you can read. Yes, one important thing is there. So when we talk about this mineral beneficiation process,
Yes, sir.
Yes, sir.
So, first question is high density of matter is related to. So, what is the property which is directly related to the high density of the metals? One thing I can tell you is all questions are from your side only. No question outside from that slide. So,
Strong metallic
big
force.
inductions has high density or closely packed atoms due to the presence of covalent ions or strong metallic force. What is directly related to the high density of metals?
A strong metallic force.
Strong metallic forces. No, I don't think so. Strong metallic forces generally uh, considered for those like electrical and electrical conductivity and the heat conductivity only. Or we can say due to the presence of mobile ions, electrical and sorry, strong metallic forces are responsible for the activity and malleability of that particular metal sheet. While presence of covalent ions are responsible for your electrical and heat conductivity, and the molecular interactions are just responsible for your like bond formations with others. So the closely packed atoms, this is the phenomenon which is directly related to the high density of metals. Okay, having very close packed atomic structure, like for example, if we talk about iron, okay, then we talk about two different gases. One is BCC and one is FCC. So which type of iron is having high density? You know,
Sir, please repeat.
iron is having two. Iron is having two different structures according to heat treatment processes, but we can see structures here to and
Alpha iron or sir beta iron.
BCC structure.
Alpha iron in FCC.
Yes. So we will be having high density, which is going to high density.
In
In FCC, that will be having high density because your FCC is standard cubic structure as atomic density of how much?
sir 0.74 something FCC.
It's around 74%, while BCC is having a structure of
68. 68.
0.68. Yeah, 68%. Okay, so if you can closely pack atoms, okay, so that can increase the density because when we talk about the density of liquids, it is not having closely packed atoms. Or in gas, they are not having an atomic packing structure at all. Okay, so that's why they are having very low density. Okay, then coming to next question, yeah. So my statement is correct for metals. Metals have no electronic energy band gap. My statement is incorrect. Resistivity of metals increases with temperature.
बहुत होना चाहिए था सर। बहुत आया था कि जो मेटल होगा उसमें एक तो जीरो बैंड गैप आना चाहिए। उसके बाद आपने ये भी बताया था कि इलेक्ट्रिकल रेजिस्टिविटी सपोज इंक्रीज करते हैं मेटल में तो टेम्परेचर भी दोनों इंक्रीज करता है।
So both the statements are correct. And without so there are four groups: metalloids, precious metals, rare earth elements, and transition metals. There are elements, so you have to pack them. Any idea what metalloids in
Metal lead,
Base
arsenic,
metals. We know what are precious metals.
uh, gold and
Okay, so is precious
precious, AU, AG,
yes, gallium and platinum. These are precious metals that metals is metals and deep elements.
transition metal D block 0, something, once again,
Metals are anti
understand, yes,
then there are yeah, so there are elements here are cerium, zirconium,
radium,
neodymium. So the cerium
radium,
used LEDs for material while zirconium and neodymium is used in making other magnets which are used inside these hard disk drives and metals, big turbines. Maybe you have heard of wind turbines for these as a source of renewable energy source. Those wind turbines also use this permanent rare earth magnet, and the permanent rare earth magnet contains plutonium and neodymium. Okay, then there is terbium. This is also used as a source of material for wind turbine drives. Okay, so we can see, so if we like
option A,
precious metals are B for one, rare earth elements, this is C4, then transition elements, this is this, and metalloids are this, germanium, arsenic, gallium, and this. Okay,
option A,
so this
option A, according to,
A3B1, I think option B is correct. I am right because
yes, sir,
A3B,
yes, sir, yes, sir,
B1, C4, D2.
yes, sir,
Okay, then we have different groups and element. I think this is C1 and B. What is the differential barrier between them? Lithium, sodium, molybdenum, or silicon?
sir, thorium, sir, radioactive,
Sodium is what?
radioactive,
Yes, sodium is radioactive material which is generally used for this
yes,
as so as we can say as a alternative to uranium because if I don't have uranium content as much we have without for sodium, we have high quantity of sodium in molar seconds. Then molybdenum,
alkyl metals, lithium,
yeah, alkali metal is lithium. So application of lithium is generally in those battery applications and one other application was there.
silicon and ferroalloy metal,
Yeah, silicon is ferroalloy metal,
and last option D,
battery lithium is used in which applications? It can be more than one answer.
Sir, batteries and medicine.
Batteries and medicine. So batteries and sorry, batteries and medicine
yes, sir,
distinction the depression. But don't take directly lithium. Okay, if you are going to depression or something.
yes,
So
sir,
now the statement is correct for ores. Aggregate of minerals from which one or
Statement 2 is correct. Sir, all mineral are considered.
No, sir. Statement 2 is incorrect.
Sorry, sir. Sorry, sir. Sir, D. Lead galena, zinc sulfuride, ammonium gibbsite, iron hydride, Fe2O4. Hematite, hematite,
Sir, galena and
Galena
sphelerite.
sulfide.
and spectrite. So these are basically sulfide group, PVS and NS. And the main property of these two are they most of the time occur together. Okay, wherever you are going to find galena, you are definitely going to find sphelerite. Okay, and some amount of gold and silver can be also found with help. It is galena and sphelerite. It is galena and sphelerite. And what
Siderite.
okay, sphelerite and what about dolomite? Dolomite is component. Any idea?
Sir,
Hydrox.
Mg3.
Hydrox. Hydro, hydroxide.
Hydroxide. Hydroxide. I am talking about dolomite is the Cerite, we know the iron carbonate. What is dolomite? Dolomite is magnesium calcium carbonate. It is a mix of magnesium carbonate and calcium carbonate. Okay, and this we use as acetate in the during the iron and lead process along with the calcite or material. Dolomite is generally used as a material during the iron and lead, and sometimes copper cement also we use dolomite for making flux material. Flux material. Hydroxide
Limon.
limonite and element is
Gold.
because gold is a highly open material for it is like right talk about e-axis and it is on the lower side of the axis. Okay, so it is very low reactive material and it generally don't form any sulfides or oxides. Okay, so it can be basically found in the native elements. Factors affecting the commercial metal production. Right?
So all above
Both
bonus. Yes.
so there are various factors which can affect the commercial metal production. So which are some type of composites? Yes, because
Oxide and sulfide we use. Oxide and sulfide.
yes, then nature acts in different uses of the metal. Yes, with if we are considering about iron, for example, if we consider iron, okay, and we are having some in the of some ore which is having iron as a byproduct and having a composition of around 10% iron. So we will go for it or not for extending the iron spread. Right? I'm going for 10% we are already having a overcontent of 67%. So that is make for considering iron value 50% only
ore concentration, benefi- beneficiation, refining, and metal separation. Removing, sir, removing of lithium, low reactive. Yes, sir. AU. No, sir.
No, sir.
Okay, thank you so much, sir.
Thank you, sir.